Hi, this is the Science Chef. Welcome to the first part of a 4-part series on chemical equilibrium. In this video, we'll be looking at reversible reactions, dynamic equilibrium, and conditions for dynamic equilibrium. So if you want to learn about the basics of chemical equilibrium, don't leave this channel, and we'll be right back. All right, welcome back. First, what is equilibrium? From your knowledge of physics, you know that an object is said to be at equilibrium when the net of all the forces acting on it from different directions is equal to what? 0, right? So at that point, say that the body is at equilibrium or is at rest, as the case may be. Now, if you import that to chemistry, in chemistry, we say that equilibrium is said to be a state in which there is no observable change, or you can say appreciable change in the properties of a system over a period of what? Time. That is equilibrium. So from my definition, what are the keywords there? Equilibrium is the state. Then what again? Of a system. And what again? No observable what? Change. In what? In the properties of the system. The properties of the system under what condition? Over a period of what? A period of time. This is the concept behind equilibrium in chemistry. All right, let's take it further now. For equilibrium to be attained in a chemical what system, there's a condition that must be in place first. That system must be what? Reversible, right? Okay, so what do we mean by reversible? So what do we mean when we say a system is reversible? I'm very sure that from your foundation chemistry, you must have seen some equations that have this arrow. The forward and backward arrow, right? This arrow indicates reversible what? Reactions, or it indicates the condition of what? Reversibility. And a reversible reaction is a reaction that can proceed in both directions. That's forward and backward under suitable what? Conditions. Okay, so let's say reversible reaction, a reaction that does what? Proceeds in both what? It has the ability to proceed in both directions. And what are those directions? Forward and what? Backward. Forward and backward directions, right? How? Under what? Suitable conditions. Under suitable conditions. So that's a reversible reaction. A reversible reaction is represented by what? By an arrow of what? Reversibility. So if you have, let's say, an hypothetical reaction, let's say A plus B giving us what? C, right? Now A plus B giving us C is a forward reaction. It's one directional. It means that this reaction will go toward completion, right? It cannot reverse, right? However, you can also have C giving us what? A plus B, right? Now, these two reactions are both one directional. While this is a combination reaction, or you call it synthesis reaction, this is what? A decomposition reaction. Are we together? So, meanwhile, if you want to learn more about types of reactions, you can check the link in the description. We made a video on that topic where we covered over 8 types of what? Reactions. It will help you to better understand this, right? So coming back to reversible reaction, now you can see A plus B going to C, and C decomposing again to what? A and B, right? Fine. So these two reactions here are occurring independently, right? However, under suitable conditions, these two reactions can occur in the same system, right? They can occur in the same vessel. How? Let's go. Means that we combine A and B, right? We combine these two reactions, A and B will give us what? C. While at the same time, C will decompose back to what? A and B. As A and B are forming C, to get to a time where C will start decomposing back to what? A and B. So this is now your what? Your reversible what? Reaction. Are we together? So it's that unlike the first reaction where A and B, either A or B or A and B can be used up and you have only C remaining, and the second reaction where C can be used up and you have only A and B left, right? But here, in a reversible reaction, at every point in time, you always have A, B, and C in the what? System. Why? Because the reaction does not go to what? Completion. All right. I hope you understand that concept of reversible reaction. All right. So let's move on to the next concept, which is what? Dynamic equilibrium. What do we mean by dynamic equilibrium? First, let's go back to reversible reaction. We just learned that reversible reaction occurs or proceeds in both directions, right? Fine. Now, a system can be reversible, but it will not attain equilibrium, right? In other words, it can proceed in both directions, but that doesn't mean that it is at equilibrium or it has attained equilibrium. In chemistry, a system is only said to attain equilibrium when the rate of the forward reaction equals the rate of the backward reaction. Are we together? The rate, not the forward reaction being equal to the backward reaction. When the rate of the forward reaction equals the rate of the backward reaction, and the concentrations of the products and reactants remain what? Constant. In other words, they do not change. The concentrations of the reactants and products do not change. And that's what we call what? Dynamic equilibrium. So what are the key when defining dynamic equilibrium? First of all, is the what? Is the state, of course, from equilibrium of the system where what? The rate, underline, rate of the forward reaction equals the rate of the backward reaction. That's it. And of course, for the rate of the forward reaction to equal the rate of the backward reaction means that the concentrations of the reactants and products are what? Constant. That there's no change in the concentration of the reactants and products at dynamic equilibrium. Now, take note of this, that there's no change in the concentrations of the reactants and product does not mean that they are equal. No. They can be equal, they may not be equal. It's not a must that they must be equal. Remember, we said equilibrium is the state of a system in which there is no what? Observable what? Change or appreciable what? Change in the properties of the system over a period of what? Time. So one of those properties that we'll be looking at later is what? Concentration. So if the system is at equilibrium, the concentrations of the reactants and product will not change over a period of what? Time. So that is dynamic equilibrium. So the last thing we'll be looking at what? Under what conditions can a system attain dynamic equilibrium. All right, follow me. Conditions for dynamic equilibrium. For a system to attain dynamic equilibrium, first of all, the reaction must occur in a closed system, or the system must be a closed what? System. So, must be a closed system. Now, what do you mean by a closed system? In basic thermodynamics, there are three types of what? Systems, right? That's what we call an open system, an open system is where the system, let's say the reaction vessel, is open and exposed to where? The atmosphere. Let's say you are heating water from a pot, right? And the pot is open. So what happens? The molecules of the water, when it boils, can escape. The gaseous molecules of the water can escape, right? As what? Vapor, right? Into the surrounding. Are we together? And moisture from there can also enter the pot. Fine. So which means that in this open system, that's what we call what? Exchange of what? That's exchange of heat, energy, and matter. There's exchange of heat, energy, and matter in the open system. Are we together? Then there's another type of system called the closed system, which is what we are looking at here. In the closed system, the same pot of water that you're boiling, but this time it is covered so that there's no space for the water to what? Escape, right? Good. Fine. Now, what's happening here? You can see that when the pot is closed, the water boils faster, right? The water boils faster than when it is what? Open. Why? Because the saturated vapor pressure of the liquid inside the pot is reached more quickly than when it is what? Open. Are you together? What's happening here? Matter cannot escape, or the liquid molecules of water have been converted to gas, cannot escape into the surrounding, right? And the gaseous molecules of water in the surrounding cannot get into the pot, right? So it is only the molecules of water that are converted to gas that only remain in the space above and then return back by themselves. So by so doing, they exert a form of pressure on the surface of the liquid, and that's called the vapor pressure, right? And when the number of gaseous molecules of water leaving equals to the number of gaseous molecules of water returning into the vessel, we said that the system is what? Saturated. Are we together? Now, when that saturated vapor pressure equals the prevailing atmospheric pressure, right, we say boiling has what? Taken place. And the temperature at which that happens is what? The boiling point of the liquid. That saturated vapor pressure will be reached more quickly when the pot is closed than when it is what? Open. Are we together here? Fine. What can we see here? There's an exchange of what? Heat energy, because you are heating the system. So it is the heat that is making the water to what? Boil, right? But there is no exchange of what? Matter. Water cannot leave the pot into the surrounding, neither can anything from the surrounding enter the pot. Are you together? So in a closed system, which has the lid, that's the cover, there's what? There's exchange of heat energy, but there's no exchange of what? No exchange of matter. Are you together? Then the last one is what we call what? An isolated what? System. This is an isolated system. Here. This is an isolated system. This isolated system is cut off from the surrounding. there is no exchange of what? Heat. Heat will not penetrate. Are you together? Because it has been what? Isolated. You can see it has been isolated from the what? Surrounding. It is just there on its own. So if heat energy or if energy cannot be exchanged, it doesn't matter that will be transferred. No. So in an isolated system, there's no what? There's no exchange of heat. And there's no what? No exchange of matter. Are we together? So these are the three types of what system. An example of an isolated system is your vacuum what? Flask. The flask you use to store your hot water or your cold water, as the case may be. That's why that water, if it is a good one, that water can stay there for 24 hours and still what? Hot. Because there's no exchange of what? Heat. Heat is not lost to the surrounding, neither is heat gained, so it maintains the same what? Temperature. Are we together? So out of these three systems, it is the what? The closed system that will easily what? Attain what? Dynamic equilibrium. So apart from the system being closed, there will also be what? Reversible. Must also be what? Reversible, right? The system must be a closed system, or the reaction must occur in a closed system, one. Then the reaction must be what? Reversible, right? Then after the reaction is reversible, the rate of the forward reaction must equal the rate of the what? Backward reaction. Rate of the forward reaction must equal the rate of the what? Backward reaction. RF is what? Rate of forward reaction. Well, RB is what? Rate of backward reaction. Are we together? So when this is achieved, right, then at that point, the concentrations of the what? Reactant and product must be what? Must be what? Constant. That there must be no what? Change in the concentrations of the reactants and what? Products. Then the last one, the change in the standard gauge free energy of the system must be equal to what? 0. That's delta G theta of the system must be equal to what? 0. What is gauge free energy? Gauge free energy is the energy available to do what? Chemical what? Work. And it is what determines the extent to which a reaction will what? Occur. What we call the feasibility or the spontaneity of a what? Reaction. That's in thermodynamics. But that's not what we're looking at here. So when the delta G of the system is equal to what? 0, then we say that the system is at what? Equilibrium. And why is this so? Why will it be equal to 0? Because delta G theta for a reaction at equilibrium is equal to what? Minus RT in what? K. Where K here is a what? You can call it KC. Is equilibrium what? Constant, right? And when the equilibrium constant is equal to 1, we'll learn about this later in the third part of this series when we're looking at equilibrium constant. When the value of the equilibrium constant is 1, means that the system is at what? Equilibrium. In other words, the concentrations of the reactants and products are what? Equal. And when the equilibrium constant is 1, I substitute 1 into this equation, definitely delta G theta will be equal to what? 0. And that is it. So I hope that you've been able to learn more than enough in this short tutorial, right? So our next tutorial, we'll be looking at the chateliers what? Principle and the factors that affect the equilibrium position of a reversible reaction. So if you don't want to miss that, quickly hit the subscribe button and turn on your notification bell. Also, don't forget to like this video. And if you have any questions on chemical equilibrium, whether we have done it yet or not, feel free to drop it in the comment section and be sure that we will attend to it. So until I come your way next time, I remain the Science Chef. Stay safe and God bless.